Greetings, and welcome to this episode in the series of videos on working with remote sensing with ArcGIS Pro. This series is brought to you by AmericaView in partnership with Virginia Tech, the Virginia Cooperative Extension, and Virginia View. I'm Cherie Aukland, and I'll be your guide. This video tutorial series builds on ongoing and previous collaborations and contributions provided by the USDA NIFA through the ADVANCE project, the National Science Foundation, through the GeoTED UAS project, the Ohio State University, and the Virginia Space Grant Consortium. This video series is associated with the Remote Sensing with ArcGIS Pro 2nd Edition book. We will use Landsat 9 imagery in this series, and we'll also begin with Chapter 10. Links to resources for this video series, including free access to the textbook and to the videos for Chapters 1 through 9, are available in the video description below. As a reminder from Chapter 17, image enhancement is processing remotely sensed imagery to adjust brightness values represented by digital numbers to improve the image's visual qualities such as color balance, brightness, contrast between pixels, or other elements associated with image display. While radiometric and spectral enhancement operate on each individual pixel, spatial enhancement deals primarily with spatial frequency and modifies the pixel's brightness values based on the values of neighboring pixels. This chapter focuses on spatial enhancement and demonstrates two processes for spatial enhancement. The first process is dynamic. It changes the image within the viewer itself, but does not change the original file. The second process uses tools in the ArcGIS Pro toolbox and creates new image data with brightness values modified by the specific enhancement method. We begin with the Chapter 17 ArcGIS Pro project removing all but the Landsat 9 clipped composite image of bands 2 through 7, created in Chapter 15, and displayed in color infrared. With spatial enhancement, individual pixel values are changed based on neighboring pixel values. Those changes are contingent on the method you select. Let's begin with dynamic spatial enhancement methods. Let's go to the Raster tab and drop down Resampling Type to view some resampling methods. We'll demonstrate nearest neighbor, bilinear, and cubic. Now let's look at an example of resampling. Zoom in to the airport in the city of Roanoke. In nearest neighbor, the pixel is assigned the value of the cell closest to it. Nearest neighbor is the default, and it is already used in the image. To verify, we can check the layer's properties. Properties, Source, Raster Information, and in the Pyramids row, we see the method is resampling nearest neighbor. Now let's drop down the resampling type and choose bilinear. You can see an immediate change. This technique creates a smooth-looking result because it averages the brightness values of 4 cells surrounding each pixel. Remember, these are dynamic methods that change the display in the viewer, not the original data. Toggling back to nearest neighbor, notice that the outlines of the individual cells are visible as a jagged edge. The corners of the pixels are distinct, but in the bilinear image, the runways and nearby highways now appear to have straight edges. The bilinear algorithm has blended the pixel corners. Now let's change to cubic. According to the information displayed for cubic, cubic interpolates from the surrounding 16 cells. You now see an even sharper looking airport area. Let's try switching back and forth between the resampling types several times, observing the differences. So going back to nearest neighbor, here are our jagged edges. Bilinear, here are some smooth edges, and cubic, even smoother edges. Now let's try majority. This option assigns the most popular value from the surrounding 4 cells and is not a good resampling method for the airport area if definitive boundaries are needed for your analysis. Let's reset the image to the default nearest neighbor. And next we'll look at creating new data using the resampling tools in the toolbox. Convolution filtering is a process that averages small sets of neighboring pixels across an image. This filtering changes the spatial frequency characteristics of an image. A convolution kernel is a matrix of numbers that assigns a weight to each cell within the matrix. The kernel defines the size of the neighborhood surrounding each pixel. As the kernel moves across the image, the values in each neighborhood are multiplied by the weights and then averaged. The resulting value is assigned to the center pixel, and the kernel moves on to the next neighborhood. Let's begin with the filter tool. Let's go to Analysis, Tools, to open the geoprocessing pane. And let's search for Filter. And we'll choose the Filter Spatial Analyst tool. We see the usual input and output raster options, but under filter type, we have two options, low pass and high pass. Low pass and high pass both use a 3x3 filter, but low pass smooths edges and high pass enhances edges. We'll explore both methods and then compare them. For input raster, choose the composite image. For output raster, give it a meaningful name to reflect the process used to create the new raster, and run. Now let's do the same using the high pass filter and give it a meaningful name and run the tool. The two new rasters are listed in Contents and appear in the map viewer. We do have a couple of things to change. Let's make sure our new layers and contents are in stretched symbology. So open symbology for each one. I happen to have it open here, but of course you can go to raster layer symbology. And we'll change primary symbology to stretch. And the same goes for filter low, stretch. And then let's zoom to the extent of our images. And I'm going to uncheck this high stretch image and look below it. Notice the low pass filter smooths the image. And turning on high pass, only clusters of certain features are enhanced in the image. Let's zoom in to the Roanoke Airport again. I'm going to do this using a bookmark. Now you see buildings are visible along with roads and the airport runways. And now let's compare this to the low pass results. The filter tool has only these two options for spatial enhancement. Which filter is appropriate for the project depends on the purpose of the project. Now we'll look at a second tool. In the geoprocessing pane, locate the Focal Statistics Image Analyst tool. You see input raster and output raster, but with this tool you'll see several more decisions must be made. The first decisions regard the neighborhood, those cells that will affect the new value of each cell in the new raster image. Here you see the first option is the shape of the neighborhood. As you can see, the shape does not have to be a rectangle. The second decision is how large to make the neighborhood. The neighborhood is the number of pixels surrounding the individual pixel whose new value will be recalculated using the neighborhood pixels. Here you see the default values used to generate the focal statistics is 3 pixels wide and 3 pixels high. The third decision to make is which statistics to use. The information icon here explains each statistic in the list. The choice, of course, is based on the project's purpose. Now let's run a few examples. We'll compare the images once we have run the tool a few times. Start with our composite image. We'll make it a rectangle for the neighborhood, a width and a height of 3, and mean for the statistics type. We have named the output raster Focal Rect 3x3 so that we know which method was used. And run. The new data shows up in the contents. Next we'll do rectangle 5x5 and mean. We'll change the name, ensure it says rectangle, change the width and height to 5, make sure statistics type is mean, and run. I'm going to do rectangle 9x9 median and circle 6 median. Here you see several new layers in your contents pane. In the interest of time, I didn't show you the entering of the parameters for each of these layers, but you can tell by the names of the layers which process was applied. I also changed the symbology to stretch and zoomed into the entire city of Roanoke. This completes a few examples. Continue to explore on your own, comparing the images generated. Now that the tool has been run using several parameters, carefully review the images for differences between them, and consider these questions for discussion. Why is the image for the 5x5 rectangular neighborhood sharper than the others? Why would the rectangular neighborhood produce sharper images compared to using a circular neighborhood? Compare the images both in grayscale stretch symbology that we have here and true color. Be sure to review the range of digital numbers and contents, different for each result. Recall that the values are being changed, and the greater the number of pixels used as the neighborhood, the smaller the range of values. Let's compare the 9x9 and 5x5 rectangular images. Turning on the 9x9 and the 5x5, we can leave those on because it won't matter. I'm zoomed into the city of Roanoke. Be sure you have the swipe tool turned on. And let's drag anywhere on the image to reveal the rectangle image underneath. The 9x9 smoothed too much, and it appears blurry. So here's the 9x9 on top, and as I swipe across, we can see the 5x5 underneath. The 5x5 image is much clearer, and the different features are more distinct. Continue experimenting on your own with different methods, comparing the new images using swipe. We've completed the spatial enhancement with a composite image, but single bands can also be used. These can be explored on your own. Ultimately, the choice of methods depends on which is best for the specific project. Let's proceed to the final image enhancement chapter, Chapter 19, Spectral Enhancement of Landsat 9 Imagery.